Welcome back. This is our third lecture in the series talking about mirror descent. And we're going to get down to the main definition of how it is that we change the proximal term from the subgradient method. So again, recall that subgradient method tells me that xt plus 1 is equal to xt minus eta gt, where gt is an element of the subdifferential of f at xt. Again, I've said this on each of these lectures, but I'm leaving out the dependence on the set constraint. But with the set constraint, this would take the form of an additional projection. So xt plus 1 is equal to the projection onto x. The projection here means Euclidean projection of xt minus eta gt. But because it doesn't change very much, for now, I've just been sparing myself the extra writing, but we should really have this in mind. And we've seen repeatedly, this has been the theme of the first two lectures on mirror descent, that xt plus 1 is also equivalently just the argmin of eta gt transpose x plus, this is the linear, you can think of this as a linear approximation to the function, plus something that keeps us from going too far. And this is typically the Euclidean norm, or specifically when we use the Euclidean norm, we get exactly the subgradient method. Set constraint here, this is an argument over all x, but if I have a set constraint, it just becomes, the only thing that changes is this is an argument over x in my set constraint. So again, not much is changing. So we're going to change this. And by changing it, we get mirror descent. And we'll see exactly when we can do this to our advantage. In order to do this and explain what will replace it, we need to define this concept of Bregman divergence. For a convex function phi, I can define its Bregman divergence as follows. So the divergence with respect to phi between 2 points x and y is defined as phi of x minus phi of y minus the gradient of phi of y transpose times x minus y. So what does this mean? This actually has a very simple interpretation, and let me group these terms as follows. Let me group the second and third term, and then I'll have to distribute that minus sign in order to make this plus. So now a simple picture tells us exactly what this is. If phi is a convex function, and I've got my point y, and I've got my point x, then what is the first term? The first term is just phi of x, it's sitting up there. What's the second term? We can interpret the second term as the linear approximation to phi at y evaluated at the point x. So this is the second term. This is phi of y plus the gradient of phi of y transpose x minus y. And therefore, the Bregman divergence is exactly this term. I'm making things a little messy here, so let's see. One more try. This is exactly the Bregman divergence. The more curvature something has, the more Bregman divergence it has. Let's do a very simple calculation. In the simple case where phi of x is just equal to 1/2 times the Euclidean distance. So let's see what the Bregman divergence is in this case. Well, plugging in the definition, I see that the Bregman divergence between x and y is equal to phi of x, that's 1/2 Euclidean norm squared of x, minus phi of y, that's 1/2 Euclidean norm squared of y, plus gradient of phi of y. Well, what's the gradient of 1/2 times the Euclidean norm? It's just y itself, y transpose times x minus y. And grouping all these terms, rewriting, I get 1/2, I'll factor that out, Euclidean norm of x squared plus minus twice y transpose x. Then I've got minus y squared plus twice y squared. That simplifies to just plus, and you can see that this is exactly the quadratic. This is equal to 1/2 x minus y squared. So if we take phi to be the function that's 1/2 Euclidean norm squared, then the Bregman divergence is just going to be the difference in Euclidean, it's the Euclidean norm of the difference. So we get something familiar. But we're going to see several examples where we're going to take phi to be something different, and therefore we get a very different Bregman divergence. Okay, and we're going to use this directly in our definition of mirror descent. So mirror descent now becomes x t plus 1 is going to be equal to the argmin, possibly in our set constraint, of eta gt transpose x, plus previously we had 1/2 times the Euclidean norm, but now we have 1/2 times the Bregman divergence between x and xt. So if phi is equal to just 1/2 Euclidean norm squared, then we recover our usual subgradient method. But if we have something else, if phi of x is equal to, say, 1/2 times x transpose times a different matrix times x, where q is not equal to the identity, then we get a different algorithm. And this is exactly the idea that started us off in mirror descent. So this was the idea that we had in lecture 1 on mirror descent. So see the first lecture in the mirror descent series. But we're going to choose phi to be even different than these. So we'll see that we can take phi to be quite different, and we therefore really change the geometry of the space. So this is our first look at mirror descent. We're going to be trying to understand its properties through examples, and then also in the following lecture, actually deriving rate of convergence and proof for rate of convergence. But in the meantime, let's go back to Bregman divergence and get used to it a little bit and see what some of its properties are. So in part, I'm going to derive this because we'll need it. In part, just to get us used to thinking about Bregman divergence. It is a little bit familiar because it seems like it, because we saw that if we choose phi to be 1/2 the Euclidean norm squared, we get back something very familiar. But if we plug in other things, it'll be a little bit different. So just want to get used to manipulating it and seeing that it's really not that difficult. Okay, so let's, in part for exercise, again in part because we'll need it, let's show that for any convex function phi, we have this property that the gradient of phi evaluated at x minus the gradient of phi evaluated at y transpose times x minus z is in fact equal to the Bregman divergence between x and y plus the Bregman divergence between z and x minus the Bregman divergence between z and y. This is just a matter of plugging in these definitions and evaluating it. So let's just do exactly that. So from the definition, the right-hand side is equal to, the first term is equal to phi of x minus phi of y plus gradient phi of y times x minus y. The second term is equal to phi of z minus phi of x plus the gradient of phi of x times z minus x. And then the third term, which we subtract, is equal to phi of z plus, I'm distributing the minus sign here, so it's plus phi of y plus the gradient of phi of y times z minus y. Okay, so what do we see? Well, first of all, I see a positive phi of x here and a negative phi of x. I see a positive phi of z and a negative phi of z. I see a negative phi of y and another positive phi of y, so all of these cancel. And now I just have to collect all of these terms here. And this is just a matter of a little bit of accounting. So this is equal to the gradient of phi of x times x minus z minus the gradient of phi of y times x minus y plus the gradient of phi of y times z minus y. And this is equal to the gradient of phi of x times x minus z minus the gradient of phi of y times x minus z. Now I can group these together and I get exactly what I wanted. This is the gradient of phi of x minus the gradient of phi of y times x minus z. We're going to use this property, but again, the point is not for us not to worry about just plugging in the definitions. These are relatively simple things. We're going to need something else in our development of mirror descent and when we analyze it, and this is the concept of a dual norm. So where have we been using dual norms without even really knowing it? We've been using dual norms because everything we've done so far, with the exception of a few things like prox, we used L1 norm and so on, we've been using the Euclidean norm. So let me give the definition here of a dual norm. So now I'm going to use this double bar just as a generic norm. So don't look at it and think it's the 2 norm. This is just some norm. So for this indicating any norm, its dual is defined as follows. I'm going to use this lower star notation. So lower star is very frequently used to denote the dual, but in some other contexts it has a specific definition. So for example, with matrices, sometimes it denotes the trace norm or the nuclear norm. But in this case, I'll try to be crystal clear if we do need to talk about another norm that's often denoted like this. For us, this star is always going to be the dual norm unless I specify otherwise. So this is defined as the maximum of U transpose V subject to V less than 1, where this is the original norm, whatever that might have been. Okay, so this is just a definition. So let's do some examples. So let's take this equal to the Euclidean norm. Might as well warm up with something familiar. So what is the dual of the Euclidean norm? I'll put a star, I'll write it this way. So so we remember, this is defined as the max of U transpose V subject to the Euclidean norm of V is less than 1. We can just solve this geometrically. It's saying your constraint set is just a sphere. So it's saying find the point on the sphere that has the largest inner product with a particular vector. What is that going to be? Well, you can see from this picture, you're not going to pick something that is perpendicular, certainly. If you pick something perpendicular, you'd get 0 in the max. You're not going to pick something in the opposite direction, you'd get negative. No, you're going to align exactly with it and go out unit norm. So in other words, the optimal solution here is the maximizer is just equal to U divided by its norm, and the max value is therefore going to be U transpose times this V times V star. This is equal to just U transpose U divided by the norm of U, which is the norm of U. In other words, the 2 norm is self-dual. So the Euclidean norm, what we just showed, is that the Euclidean norm is its own dual. It's called self-dual. So this is the way that we've been actually using the dual norm without even really knowing it, because we've just been working in the 2 norm. So let's take another example. So now let's take, example 1, let's take norm equal to the 1 norm. And let's see what its dual is. So we've got, what is the dual norm of U in the 1 norm? This is, again, just copying the definition, the max of U transpose V, U transpose V, subject to V in the 1 norm being less than 1. So let's think about what this is going to give us. So what does this 1 norm tell us? So this constraint is telling us that we have to be inside this diamond, or algebraically, it's telling us that the absolute values have to sum to 1. You can think about this as a resource allocation problem. You have to allocate your resources, but you only have 100%. You have to allocate the pieces so that they add up to 1. Where are you going to put them? You're going to put them wherever the values are the biggest. The slight difference to this is that U can take values that are positive and negative, but then so can V. So what you're going to do is you're going to find the biggest in absolute value element of U, whether it's positive or negative, and you're going to heap all of V, all of your energy, you're going to put onto that coordinate. If the biggest element of U is negative, you're also going to make V negative. If the biggest element of U is positive, you're also going to make V positive. So in other words, V star in this case, or optimizing V, is going to look like the vector that's all 0 except with a single 1. And it's going to have a single 1 in the ith position, and its sign is going to be the sign of ui. And which I is it going to be? It's going to be the I where the value of the absolute value of ui is biggest. So I is the argmax of the absolute value of ui. So in other words, what do we get? The dual norm is the infinity norm. So the dual norm of U is just equal to the infinity norm. And you can also see that the infinity norm, its dual, is going to be the 1 norm. So there are many examples like this that we can work out. Let's do one more example. So far, we've seen that the dual of the Euclidean norm is, again, the Euclidean norm. The dual of the one norm is the infinity norm. I mentioned that the dual of the infinity norm is the one norm. So let's try that. So the infinity norm, let's look at the dual of that. By definition, this is the max of U transpose V subject to V in the infinity norm being less than 1. So the infinity norm being less than 1 means that every element of V can be between -1 and 1. And there's no penalty. In other words, if V1 is very big, it doesn't mean that V2 has to be small. So what would you do? Again, you can see this is quite simple. You would look at UI and say, UI, is that positive or negative? I'm going to let VI be the same sign and be as big as I'm allowed, which is in this case 1. So the optimizing V is just going to be the sign of U, element-wise. In other words, the ith element of V star is just going to be the sign of UI. And so then what is the sum of, so U transpose V is equal to the sum of UI VI. And plugging in this V, this is the same as the sum of UI times the sine of UI, which is exactly equal to the sum of the absolute value of UI, which is in fact the L1 norm. So now we've seen all three of these examples, and we're going to use a very important property of dual norms, which I'm going to write down now, and we're going to see it again in the next lecture. So an important inequality says the following. Remember that we've needed to bound several times the dot product between two vectors, u and v. And we've done this in several ways. So we can bound this in terms of the 2 norm. So this is upper bounded by the 2 norm of u times the 2 norm of v. In fact, we know that these are equal only when u and v are parallel and pointing in the same direction. So this is the Cauchy-Schwarz, famous Cauchy-Schwarz inequality. Now, in fact, it's also true that U transpose V is less than or equal to U times V star, where U and V are any norm and its dual. And this is sometimes called Hölder's inequality. Now, so far we've used, if you go back to the proofs of gradient descent, subgradient descent, and so on, you'll see this kind of inequality, the first one, in many places. So one of the properties that we've used, another way to bound UV is as follows. Also, U transpose V is less than or equal to 1/2 times U squared, this is Euclidean norm squared, plus 1/2 V squared. This just comes from completing the square. Again, we've used this over and over again. But using the dual norm, we can refine this in a particular way. So we will use the following. Upper bound. U transpose V is less than or equal to 1 over 2 alpha times the norm of U squared. Note there's no 2 subscript. This is not the Euclidean norm. Plus alpha over 2 times the dual norm of V squared. And this is very similar If we take alpha equals to 1, we recover what we get from completing the square. The reason that this is so important for us is that these dot products are foundational for us. This is the definition of convexity. We use these to make our linear approximations. This is how we define convex functions. This is how we define our linear approximations. And this is how we define all our algorithms. So we're going to see next time how we use this inequality, how we use Bregman divergence, and how we use the definition of the Bregman divergence as a proximal term in order to show better convergence rates for mirror prox in certain settings where, for mirror descent, in certain settings where we don't want to use Euclidean geometry. We'll pick this up next time.